Hello friends, I welcome you in lecture number 39 on Laplace transform. In lecture number 38 we have discussed about convolution operation between two functions. So we just recall the definition of convolution of two functions f and g. It is denoted by f star g of t and is defined as integral from 0 to t f of u g of t minus u integral with respect to u. In this lecture we are going to discuss that how to obtain Laplace transform of the convolution of two functions without using this definition. Suppose I want to obtain Laplace transform of convolution of f and g, then one way is, first I will decide what is this function of t. I will integrate this f of u g of t minus u with respect to u from u equal to 0 to t, and I will obtain some function of t, and then I will obtain Laplace transform of that convolution. But we have one result which says that we can directly find out Laplace transform of convolution without obtaining this function using this definition. So that result is called convolution theorem, and it is very easy to remember convolution theorem. Suppose we are interested in the Laplace transform of convolution of f and g, then convolution theorem says that this is nothing but product of Laplace transform of two functions f and g. So Laplace transform of convolution f star g equal to Laplace transform of f into Laplace transform of g, and we can denote Laplace transform of small f by capital F of s, Laplace transform of small g by capital G of s. So this is very helpful result. It is known as convolution theorem. Sometimes they ask you to write down the statement of convolution theorem, and you can write in this way: if Laplace transform of small f of t is capital F of s and Laplace transform of small g of t is capital G of s, then Laplace transform of f star g equal to product of f of s and g of s. Using convolution theorem we find out Laplace transform of these two functions, which are convolutions of two functions. First function is convolution of t and e raised to t. So by convolution theorem I can simply write this is equal to Laplace transform of t into Laplace transform of e raised to t, and here we mention that by convolution theorem, and we have ready-made formulas for the Laplace transform of these two functions. Laplace transform of t is 1 divided by s square, and Laplace transform of e raised to at is 1 divided by s minus 1. Here we are using this formula. Laplace transform of t raised to n is n factorial divided by s raised to n plus 1, and here power is 1. So we put n equal to 1, and Laplace transform of t is 1 by s square. Laplace transform of e raised to t is 1 by s minus 1. So this is very easy. You just have to multiply Laplace transforms of two functions, and if you wish you can verify. We can just find out t star e raised to t, and if I am not wrong we have obtained this t star e raised to t in previous lecture. Let me check. In this lecture number 38 we have obtained t star e raised to t. So I put value of t star e raised to t from that lecture. It is e raised to t minus 1, e raised to t minus 1, that we substitute here, and we check whether this is correct or not. This we have obtained. If you have not seen, lecture number 38. Then you can see lecture number 38. We have obtained this convolution using the definition of convolution, and we are interested in the Laplace transform of t star e raised to t. This is equal to Laplace transform of e raised to t minus 1. Laplace transform of e raised to t is 1 minus 1 upon s minus 1. Laplace transform of t is 1 by s square. Laplace transform of 1 is 1 by s. And we can take LCM as s square into s minus 1. So here we have to multiply by s square, here s minus 1, and here s times s minus 1. And we simplify this. This is s square minus s plus 1 minus s plus 1 minus s square plus s. So and denominator is s square into s minus 1, and you can see s square will cancel out, s will cancel out, and Laplace transform is 1 divided by s square times s minus 1, which is same as we have obtained using convolution theorem. So this is just to explain you the power of convolution theorem. Here we don't have to evaluate this t star e raised to t. Without evaluating or without obtaining convolution of t star e raised to t, we are able to decide the Laplace transform of convolution of t and e raised to t. And this is another way. Here we have obtained this t star e raised to t by the definition of convolution, and then we obtain the Laplace transform and we get the same answer. Okay, fine. Now we can obtain Laplace transform of convolution of sin omega t and cos omega t using Laplace transform. So second question is Laplace transform of convolution of sin and cosine omega t, where omega is constant. So again, by convolution theorem, this is equal to Laplace transform of sin omega t multiplied with Laplace transform of cos omega t, and in the bracket we must specify that we are using convolution theorem. This is by convolution theorem, and we know that Laplace transform of sin omega t is omega divided by s square plus omega square. Laplace transform of cos omega t is s divided by s square plus omega square, and this we can rewrite as omega into s divided by s square plus omega square whole square. So in this way we can obtain Laplace transform of convolution of two functions using convolution theorem. But remember, do not misunderstand in this way. If I have product of two functions f and g, then this result is not true. Laplace transform of f into Laplace transform of g. This result is not true for the product operation between two functions. So be careful, this is danger. Instead of that, this result is true for the convolution operation. For multiplication operation, result is not true, but it is true for the operation of convolution between two functions. So this is always correct, and for product this is not correct. So never use this result. Okay, it is true for convolution operation. So in this lecture we have discussed about convolution theorem. In the next lecture we will discuss convolution theorem for inverse Laplace transform, and that will be helpful for finding inverse Laplace transform for product of two functions. So this is all about this session. I hope you like it. Thank you very much.